right, students, today we're going to do a few more applications of quadratic equations. These are going to have to do with rockets or maybe launching something off a roof and seeing how long it takes to hit the ground, finding its maximum and minimums. So we're not even going to worry too much about that, but we're going to at least look at some quadratic equations that deal with that kind of information. So here we go. So this is applied problems that we're going to do. Well, was that the end? Why? Oh, just two slides. Well, I guess we're not going to worry too much about that. Uh, seems that there's only two, but I'll give you a couple. We'll think of a couple that we could do. 1 second though. I'm not sure where all my quadratics went, but let's look at what a few of those could be. So back to my Zoom here. No, that's not what I want. I want my Zoom here. Okay. Let's go ahead and share. I did share you are shared. Make sure that's working out. Get to cancel that. Okay. So here we are. Going to stop that share. I'm going to reshare it with you. And you can just see a couple of these because I know that you're going to see them in the homework, what we need to do. So you're going to use given formulas to apply them. And so let's look at some ideas about physics in the world. Whenever you launch something into the air, physics, the gravity of the Earth is always pulling on it a negative 16 t squared. And what that means is it's dropping to the Earth at 16 feet per second squared. So the more time that it's falling, the faster it's falling, and it's going to land on Earth. So most of your problems are going to have this number in them, okay? Let's go ahead and look at some. So let's say that you and I were up on a building and we were launching water balloons off of the building and hitting people below us, but we were kind of launching them with a slingshot. So we have this building here. And let's say it's 20 feet off the ground from here to here. Okay, and here's the ground. So this is 20 feet. And we're launching it, and it's going to go up at some point, up. And eventually, gravity is going to stop its forward progression, and it's going to start pulling it to Earth. And at some point over here in t seconds, it's going to hit the Earth. So this side right here is the height, and this is the time that it takes, to go there. So we could maybe write a formula that would look like this. And let's say that our rocket launches it at 50 feet per second, okay? So our launcher's pretty powerful, 50 feet per second. So we're up on this building, and we launch it, and we're going to call the height, whatever the height is, based on time. Let's do h of t, height based on the time, okay? So this is h, this is t. And we know that gravity is going to be pulling on it at that. That's a given. We know that that's happening. We also know that we actually launched that at 50 feet per second, but we don't know how many seconds are going to be happening. And what was the height that we started at? We didn't start at ground level, did we? We started at 20 feet off the ground. And so that is our equation that we're going to do. And so I could ask you several things. I could say to you, how high will this get? Its top here. This is called its maximum. And we'll learn about a little bit later on how to do that. But I could say at 0, how high is the water balloon? So if I put 0 and 0 in for time, we know it's 20 feet off the ground. I need to find when will it hit the ground? What if I wanted to find where it hit the ground? Well, where it hits the ground happens to be a 0 or an x-intercept or the word solve. I'm solving for these x's here. And so I could just go ahead and factor this, and I could say, When it hits the ground, its height is 0. And now look at that. I have this big, fat, nasty equation that I could do, and I could solve that. And then I could try to factor that. And this one's not going to factor that pretty, but this is one of the applied things that we could use for that, and that we could apply it that way. We could also apply it with rockets being launched off the ground, and they get launched into space and they go up so far, and then they're going to come down. And we could even determine how far away they ended up after when they hit the ground. How far away were they? We could determine that distance, how much it traveled. There's several things that we can do. If you remember the show October Sky, the young man, he launches his rocket and it goes up and then it comes down, and the people of the train say, "Oh, your rocket started a fire and it caused all this damage," and he kind of gets in big trouble. Well, the kid's like, "I just don't think my rocket did it." He's like, "It was the train that did it." And so he proves mathematically using quadratics and some other information but he knows about that, and he knows his mathematics, that he proves that this couldn't have been my rocket. In fact, he's able to find his rocket based on where it was, the angle of its launch, it's how fast it was, the speed of it when it launched and everything, where it would have landed. And sure enough, he finds where it would have landed, and it's nowhere near the burn site of what they thought his rockets were doing. And so he proves himself innocent there. He goes on to become world famous in the terms that he works on the space shuttle and he gets it into space and rockets into space. And so it's a kind of a really cool coming of age movie for a boy who's out of the coal mines. That was his option in life. And he's like, no, I want to learn more and learn about the mathematics and do what drove him. And that was it. Anyway, good movie to watch, October Sky. But that's how you can apply these problems. So we're not going to go any further with that. I'm going to look a little bit. Hold on one second. We're going to take a pause, actually. And let's see. Pause it here. I'll be right. All right, so let's look a little bit about this problem that I've made you. And what if I asked you, um, let's go back and let's draw a problem here. I'm going to clear that slide off. Back it up here. Come on. No, it kept it. Okay, what if I get this going from... Okay, what if I said, how high would this be when after 2 seconds? How high would my water balloon be after 2 seconds? Okay, and so I would put a 2 in here. Negative 16 times 2 squared plus 50 times 2 plus 20. And 2 squared is 4, and 4 times a negative 16 is what? A negative 64. So a negative 64 plus 100 is 36 plus 20. It would be 56 feet high. So we're like, remember we were here, we're going to be 56 feet high somewhere. We don't know if it's on its way down or not, but then what I said, well, what would it be after 4 seconds? How high would it be after 4 seconds if the time were 4 seconds? Would it have landed on the ground? So we put 4 in there. And 4 squared is 16, and 16 times 16 is what? I think it's 236. Let me grab my, not quite sure on that. 16 times 16. Let me quickly calculate that. Open my calculator here. 256. That's a negative 256 plus 200 plus 20. That tells me that it's in the negative. It's gone into the earth. So somewhere between 2 and 4 seconds, that water balloon is going to land, isn't it? So we could try like 3, but we could just say where it was at that given point. What about 1 second? Where do we see it? Suppose that this water balloon was at 1 second. So I put a 1 in there. Oops. And 16, this is a negative 16 times 1. 1 squared is 1, so a negative 16 plus 50 plus 20, that's going to be 54 feet. So it's going to be 54 feet somewhere. So we had 50, so at 1 second it's at 54 feet. Maybe it's come up and hit its top and now it's headed down. It's 56 feet after 2 seconds. But after 3, it's hit the ground, hasn't it? And so you can kind of use information like that. You're going to see problems where they're launching a cannon out of a cannon, or you're trying to find the volume of something. And so you're going to actually know, you're going to figure out this equation. They'll actually give it to you. You don't really have to figure it out. You just have to substitute values in for t and answer their questions, okay? They're not even asking you to find the zeros. They're not even asking you to find where it hits the ground. We could have one where it hit the ground, but they're not, I don't even think they ask you that. So there's 5 questions that they're going to ask you. It's really more about solving, putting a variable in for t and finding out what the height is, or what the speed is, or what the volume is on something. So go ahead and give that a whirl and see how you do, and we'll talk to you later. Have a good day.